Today, we're plunging into a world where, well, an invisible flaw can undermine an entire structure. It's the fascinating and sometimes frustrating topic of steel weldability. Imagine a complex dance between metal, heat, and chemistry. A dance that dictates if a weld holds strong or, tragically fails.
That's a good way to put it.
Our mission today is to cut through the jargon, really reveal the crucial factors and the hidden imperfections that dictate a steel's ability to be joined soundly.
And this knowledge is, well, it's far more fundamental than you might initially think. Understanding weldability isn't just for engineers toiling away in labs or factories.
Right.
It's absolutely vital to the safety and reliability of countless structures and products we interact with every single day.
Like what sort of thing?
Think about it.
Yeah.
The cars we drive, the bridges we cross, the buildings we inhabit, even the everyday tools in your garage, they all rely on strong, defect-free welds.
Huh. You don't often think about the weld specifically.
Exactly. So a deep dive into these intricate mechanisms helps us appreciate the hidden complexities behind these seemingly simple connections, and why sometimes that connection isn't quite as simple as it looks.
Okay, let's unpack this then. We're talking about weldability. At its simplest, what exactly does that term encompass? And what makes a steel good or bad at it?
Right. At its core, weldability is basically a steel's ability to be joined effectively with suitable properties and, crucially, without defects.
Without defects, that's key.
Absolutely. Steels can have good or poor weldability depending on how easily you can achieve those results. When we say a steel has good weldability, it means you can often weld it quite straightforwardly, fewer headaches. But poor weldability, that means you're going to need to take some serious precautions. You might have to work within very narrow welding parameters to get a reliable joint. It gets tricky.
So it's about the ease and reliability of making that connection. What are the big factors that influence this?
Well, the ease or difficulty, that defines its weldability. And there are a number of interrelated factors that determine this.
Such as?
First, the steel's actual chemical composition, what it's made of, right down at the microscopic level. Then the specific geometry of the weld joint itself, how the pieces fit together. Also, the welding process you're using, stick welding, TIG, MIG, automated processes, they all behave differently. And of course, the properties that are actually required from the final weldment. What does it need to do? Right,
the end goal.
Exactly. And for steels with poor weldability, it becomes incredibly important to have rigorous weld procedure specifications, WPSs.
WPSs, like a recipe.
Pretty much. Like detailed recipes that give welding conditions designed specifically to prevent cracking while still hitting all the necessary strength requirements.
Gotcha.
And it's not just about the procedure on paper. The welders must stick to it religiously, and inspectors need to be diligently monitoring to ensure that adherence is maintained. It's a chain of precision, really, where every link matters.
So if weldability is all about creating these sound, defect-free welds, where do things typically go wrong? My guess is it often comes down to cracking.
You've hit on a critical point there. Very often, it comes down to cracking. And what's truly fascinating here, a real aha moment for many, is that for any type of cracking mechanism to occur, there's a powerful, unifying concept at play. Certain foundational elements must always be present simultaneously.
Okay, wait. So you're saying there's like a common formula for cracks? That's a huge insight. It sounds like a universal equation for failure. What are these core conditions?
Exactly. Think of it like a three-legged stool. For cracking to happen, you need these three conditions. First, stress. And let's be clear, residual stresses. The kind left over from the vessel expanding and contracting unevenly during welding. They're always present in a weldment.
Always. Okay.
Second, you need restraint, which is basically how rigid or restricted the components being welded are, locally or overall. How much can they move?
Rigidity.
And third, you need a susceptible microstructure. Essentially, the material itself is made vulnerable to cracking by the welding process. It can become hard and brittle in certain areas.
So stress, restraint, and a vulnerable structure.
Those are the big three. Now, for some specific crack types, temperature also plays a critical role. But those core three, always there.
Wow.
Understanding this framework simplifies what can seem like incredibly complex problems into a common, understandable pattern. It means we don't need 100 different solutions. We just need to break one of those links in the chain.
That's brilliant. It means even though there are different types of cracks, they all share common threads. With that in mind, let's maybe meet the most common culprits, the ones that threaten a weld's integrity. First up, this sort of silent, delayed threat. Hydrogen cracking.
Ah, yes, hydrogen cracking. Or, technically, hydrogen-induced cold cracking, HICC.
HICC, heard of it.
Yeah, but you'll often hear it referred to by many names that describe its characteristics, like cold cracking, because it occurs when the weld is cooled down.
Makes sense.
Or HAZ cracking, because it primarily occurs in the heat-affected zone.
The HAZ, that's the part of the parent metal right next to the weld, the bit that gets hot but doesn't actually melt.
Exactly that, and it's particularly vulnerable. Then you might hear delayed cracking.
Ah, this is the sneaky part you mentioned.
This is the sneaky part. It can literally show up hours later, sometimes up to maybe 72 hours after welding is finished.
72 hours, wow. Days later.
Yeah, truly sneaky. And sometimes under bead cracking if it's in the HAZ just beneath a weld bead. Now, while it mostly appears in the HAZ under certain circumstances, it can even form in the weld metal itself.
Okay, so it's a crack that can appear seemingly out of nowhere, sometimes days later. And you said for HAZ hydrogen cracking, 4 conditions must exist simultaneously. Can you break those down for us?
Absolutely. Think of them as necessary ingredients that all have to be in the bowl at the same time. You need 1, hydrogen present, not a huge amount, but enough to cause trouble.
Hey, hydrogen.
2, stress. Particularly high tensile stress, the kind that pulls material apart.
Right, tensile stress.
3, a temperature below around 300 degrees Celsius, so relatively cool.
Below 300 C, got it.
And 4, a susceptible microstructure, meaning the metal has become very hard and brittle, almost like glass, often indicated by high hardness measurements.
Hydrogen, stress, low temp, brittle structure.
That's the quartet. And these factors are mutually interdependent. If you change one, it impacts the others. For instance, if you manage to really reduce the hydrogen, you might be able to tolerate a harder microstructure than you otherwise could.
Okay, here's where it gets really interesting for me. So how do these 4 factors actually work together to create a crack? Is it like a tiny explosion or something more subtle?
It's much more subtle. Think of hydrogen atoms. They're incredibly tiny. They form when hydrogen-containing molecules, like moisture in the welding flux, or even rust and oils on the material.
Contaminants.
Exactly. When those break down in the heat of the welding arc, you get these tiny hydrogen atoms.
Yeah.
They then enter the molten weld pool.
Okay.
Now, while the weld metal is hot, these atoms are incredibly mobile. They can sort of swim quickly through the metal grid and escape to the surface, like steam rising from a pot.
Right, they diffuse out.
But as the weldment cools rapidly, especially down to ambient temperature, that hydrogen can become trapped, usually in that heat-affected zone, the HAZ.
They get stuck.
They get stuck. And if that HAZ has a susceptible microstructure, meaning it's relatively hard and brittle, and there are also high tensile stresses in the weldment, then that trapped hydrogen causes embrittlement.
Embrittlement makes it fragile.
Exactly. It makes the material so fragile that the existing stresses cause it to crack, rather than just stretch or deform plastically like it normally would.
Wow. So the key to avoiding this silent, delayed threat is basically making sure at least one of those 4 conditions isn't active. What are the most practical ways to do that in the real world?
Well, if there's one golden rule for hydrogen cracking, it's probably keep it dry and keep it warm.
Dry and warm. Okay.
So first, reducing hydrogen. This is the most direct approach. It means using low hydrogen consumables like welding rods. Often involves baking electrodes or keeping them in vacuum-sealed packages.
Right, like keeping gunpowder dry.
Kind of, yeah. For processes like submerged arc welding or at saw debber, where you've got that granular flux covering the weld, basic agglomerated fluxes need to be kept in heated silos. And crucially, the weld zone itself must be pristine.
Pristine?
Clean and dry, free from rust, scale, oils, grease. All that stuff is a potential source of hydrogen.
Makes sense. What about stress?
Okay, reducing tensile stress. Now, residual stresses are, like we said, always present due to welding's nature. But we can mitigate stress concentrations.
How?
By ensuring good fit-up of the parts before you weld and avoiding sharp weld toes. Basically, designing the joints to avoid stress hotspots. Sometimes a post-weld stress relief heat treatment can help reduce these stresses after everything's cooled down.
Heat treatment after welding.
Okay.
And the microstructure.
Right. Avoiding a susceptible HAZ microstructure.
Right.
For steels like carbon and carbon manganese steels, the chemical composition and, importantly, how fast it cools determines how hard the HAZ becomes.
Cooling rate matters.
Hugely. There's something called the carbon equivalent value, or CEV. It's a formula that helps predict this hardening potential based on the chemistry. Higher CEV generally means more susceptible. Carbon itself is a major player here.
So how do you control that hardness?
Well, using a moderate welding heat input helps slow down the cooling rate, preventing that rapid hardening. Applying preheat warming the metal before welding or maintaining specific interpass temperatures in multi-run welds also slows cooling. Slower cooling generally means a softer, less brittle HAZ. It's a bit trickier with some low alloy steels, though. Their HAZ tends to get hard regardless.
Okay, preheating helps. And the last factor was temperature control.
Yes, controlling weldment temperature.
Yeah.
Basically, keeping the weld relatively warm, generally above about 300 Celsius, allows that mobile hydrogen to diffuse out quickly rather than getting trapped as it cools.
So keep it warm for longer.
Pretty much. This can be achieved by applying a suitable preheat, typically warming the metal somewhere between 50 and 250 degrees C before welding. Preventing rapid cooling after each pass is also important, and sometimes applying what's called a post-heat, holding the joint at around 250 degrees C for at least 2 hours after welding, helps any remaining hydrogen escape.
Preheat, controlled cooling, maybe post-heat, lots of temperature management.
It's often critical for preventing hydrogen cracking.
That's a really clear, multi-pronged attack on hydrogen. And you also mentioned hydrogen cracks can pop up in the weld metal itself sometimes. You call them chevron cracks.
That's right, yeah. Because of their distinctive 45-degree angle appearance. These are often seen in higher strength materials or maybe thicker sections. Just another challenge to ensuring a strong connection.
Okay. So while hydrogen cracking might sneak up on you hours later, our next problem, this one rears its head almost immediately, right as the weld is cooling, solidification cracking.
Exactly.
Also called hot cracking, or sometimes centerline cracking. It literally forms as the weld metal solidifies.
That's right. And for solidification cracking, again, there are conditions that must exist simultaneously. Typically 3 this time.
Okay, what are they?
First, the weld metal has a susceptible chemical composition. It's just prone to this problem. Second, the welding conditions result in an unfavorable bead shape. And third, there are high levels of restraint or tensile stresses present in the weld area as it cools.
So susceptible metal, bad bead shape, and stress again.
Stress is often part of the equation, yes. If a weld metal is particularly susceptible, it can be described as showing hot shortness.
Hot shortness.
Yeah, it means it lacks ductility, the ability to stretch or deform without crapping when it's hot. So it just tends to crack instead.
Gotcha. So what's the precise mechanism at play here? How does the weld crack as it's cooling down right there and then?
Okay, picture the molten weld pool. Cooling. Solidification starts in the edges, the fusion line where the liquid weld meets the solid parent metal, and it grows inwards toward the center.
Right. Solidifies from the outside in.
Exactly. The very last parts to solidify are typically right down the center line. And this is where low melting point impurities, things like iron sulfides from sulfur contamination or even tiny copper films.
Impurities again.
Impurities again. They get pushed ahead of the solidifying front, like snow clouds pushing snow. These impurities concentrate in the last bit of liquid, forming these weak liquid films between the newly formed solid grains.
Liquid films trapped inside.
Trapped right at the center, often. Then, as the surrounding solid material continues to cool and contract, it pulls on these weak liquid films. They're put under intense tensile stress, and they simply don't have the strength. They rupture.
They tear open.
They tear open, and the result is a crack, often visible almost immediately after the welding torch moves on, usually right down the center of the weld bead.
So the secret to avoiding these hot cracks is tackling those 3 conditions.
Pretty much, yes.
Yeah.
First, weld metal composition. The absolute key here is to avoid contamination. Sulfur and copper are particularly nasty culprits for this.
Where do they come from?
Sulfur often comes from oil, grease left on the joint, or sometimes from less refined parent steel grades. It forms iron sulfides that stay liquid at very low temperatures relative to the steel. Copper, maybe from contact with copper tooling or backing bars, can form films that remain molten even at temperatures around 1100 degrees C.
Wow, that high.
Yeah, so thorough cleaning of the weld joints immediately before welding is absolutely crucial. You want to prevent these low melting point films from forming in the first place. It's truly amazing how a tiny bit of dirt or grease can cause such a massive problem.
Cleanliness is critical. What about the bead shape?
Right. Second point, unfavorable welding conditions related to bead shape. Imagine a really deep, narrow weld bead, almost like a canyon. These shapes tend to trap those weak liquid films right at the center, at the warrant.
Makes sense. Nowhere for them to go.
Exactly. In contrast, think of wider, shallower beads, more like a broad, shallow river. These shapes tend to push the liquid films up towards the surface as the weld solidifies. Once they reach the surface, they can often kind of self-heal or just form a minor surface imperfection rather than a crack deep inside.
Interesting. So bead shape matters a lot. Are some welding processes worse for this?
Yes, some processes tend to produce those deeper, narrower beads naturally. Things like submerged arc welding, spray transfer GMEW, or MIG welding, electron beam and laser welding, they can be more susceptible.
So how do you fix it?
You adjust your welding parameters. For instance, you might reduce the welding current to get a shallower bead, or maybe reduce the welding speed to get a wider bead. You're aiming for a better width-to-depth ratio, ideally less than, say, 1:2.
Less deep than it is wide, roughly.
That's the idea. And a specific form of this is crater cracking. It happens right at the very end of a weld run where the arc stops.
Ah, a little dip at the end.
Yeah, that crater, it solidifies last and can easily crack. To avoid those, there are specific techniques. Like with TIG welding, you use current slope out, where the current and the weld pool depth gradually reduce before the arc extinguishes.
Gently fades out.
Right. Or in manual metal arc welding, stick welding, you might briefly reverse the travel direction right at the end of the run. Just backstep slightly to fill the crater properly before pulling the electrode away. Very effective.
Fascinating how the shape of the weld bead, even down to the finish, can be so critical. Okay, now let's talk about a crack that doesn't occur in the weld metal or even the immediate heat-affected zone, but in the parent steel plate itself.
Lamellar tearing.
Ah, yes, lamellar tearing.
This is distinctive, right?
Yeah.
Because it usually happens underneath the weld, has that weird stepped appearance, and tends to lie parallel to the material surface, mostly in carbon manganese steels.
You've described it perfectly. And yes, it's a peculiar one because it's a failure of the plate material induced by the welding stresses. Lamellar tearing requires two specific conditions to occur simultaneously.
What are those?
You need 1, a susceptible rolled plate. The plate itself has an inherent weakness. And 2, you need high stresses acting in the through thickness direction of that plate material.
Through thickness. So
Yeah.
pulling the plate apart through its thickness, like trying to split a piece of plywood.
Exactly. That direction is also known as the short transverse direction. It's the direction the plate is weakest in, usually. So what makes a plate susceptible to this kind of tearing? What's going on inside the steel itself?
Okay, a susceptible plate has very low ductility, very little ability to stretch or deform, specifically in that through thickness direction.
Why is it weak in that direction?
It's caused by the presence of numerous non-metallic inclusions, things like manganese sulfides and silicates, which are leftovers from the steelmaking process. During the hot rolling process, when the steel slab is flattened into a plate, these inclusions get squashed and elongated into flat stringers.
Like stretched out impurities.
Exactly, almost like microscopic layers of weakness within the plate, all lined up parallel to the surface. So when stress is applied in that through thickness direction, the plate doesn't stretch nicely. Instead, it tears along these weak inclusion stringers.
Ah, they act like perforations.
That's a great analogy, yeah. It's like trying to pull apart a deck of cards sideways. It's much easier than pulling them lengthwise where the fibers run.
Okay. And where do those high through thickness stresses come from?
They usually arise from specific joint configurations, particularly T, K, and Y joints. Think of them like intersections where plates meet at angles, often welded all the way through.
Like structural joints.
Very common in structural steelwork, yeah, especially in thick sections and where you have full penetration welds. The more rigid or restrained the joint is, the greater the magnitude of that residual through thickness stress pulling on the plate face underneath the weld.
And the mechanism sounds almost, well, simple once those elements are in place. The stress pulls on the stringers.
Pretty much. The through thickness residual stresses cause the inclusion stringers to decohese, basically.
Yeah.
The interface between the inclusion and the steel opens up. And then the thin ligaments of steel between those opened up inclusions tear under the stress, creating that characteristic step crack appearance, linking up the inclusions.
Step-by-step tearing.
Exactly.
So how do we avoid this? It sounds like the plate itself is the problem.
Often, yes. So the best prevention starts with procuring less susceptible rolled plate, basically using higher quality material.
How do you specify that?
You specify clean steel with low sulfur content, typically less than about 0.015% sulfur. Lower sulfur means far fewer of those problematic manganese sulfide inclusions.
Okay, low sulfur steel.
And you can also perform through thickness tensile testing on the plate material. You measure the percent reduction of area when pulled in that direction. Values over about 20% generally indicate good resistance to lamellar tearing.
So you can test for it.
You can. Beyond material selection, though, you can also modify the joint itself to reduce that through-thickness stress on the susceptible plate.
Like changing the design.
Sometimes, yes. Or it might mean reducing the required weld size, perhaps using a partial penetration butt weld, or even fillet welds instead of a full penetration weld if the design allows. Less weld metal means less shrinkage stress.
Makes sense.
Another clever technique is applying a buttering layer. Yeah, you deposit a layer of soft, ductile weld metal onto the face of the susceptible plate before making the main structural weld. This buttering layer acts like a cushion. It deforms easily and shifts the highest strain concentration away from the vulnerable parent plate material and into the more forgiving weld metal.
Neat trick.
It can be very effective. Or, for truly critical applications, you might need to change the joint design entirely. Maybe use a forged or extruded intermediate piece, like a specially shaped nozzle or stub, so you're not welding directly onto the susceptible plate surface in that critical orientation. It's all about redirecting that stress away from the weak direction.
Lots of ways to tackle it then, from material choice to clever joint design. Okay, our final deep dive for today shifts gears a bit. We're moving from immediate fabrication defects to a problem that can appear much later, sometimes long after the component is in service. Weld decay.
Weld decay, yes, a different beast altogether.
This is unique to stainless steels, right? Primarily certain types, and it's caused by corrosion.
That's correct. Primarily affects some austenitic stainless steels. And yes, it's a service failure mode, caused by corrosion, not usually something you see right after welding.
So what does it look like?
You'll see it as a narrow, severely corroded zone in the heat-affected zone, right alongside the weld. Meanwhile, the weld metal itself and the parent metal further away might look perfectly fine. It's like a hidden disease that suddenly eats away at a very specific area.
Wow. So what are the conditions for this?
Weld decay requires two conditions. First, a sensitive HAZ, that heat-affected zone next to the weld, has been made vulnerable. And second, contact with a corrosive liquid during service. The environment has to be aggressive enough to attack the weakened area.
And what makes the HAZ sensitive? What's the core mechanism?
Okay, this typically occurs in standard grades of austenitic stainless steel that are not the low-carbon grades. So think regular 304 or 316 as opposed to 304L or 316L. The L stands for low carbon.
Got it. Standard grades.
When these standard grades are heated during welding, particularly when they spend time in the critical temperature range of around 600 to 850 degrees Celsius, chromium carbides form at the grain boundaries within the HAZ.
Chromium carbides, okay.
The chromium is the key element that gives stainless steel its corrosion resistance, its stainlessness. When these carbides form, they use up the chromium from the areas immediately surrounding the grain boundaries. This process essentially steals the chromium, locally depleting those zones.
So the boundaries lose their protection.
Precisely. Without enough chromium right at the grain boundaries, the steel's natural rust-proofing is compromised in those very narrow bands. And the more weld runs you do, or the thicker the section, the more time that HAZ spends cooling through this critical temperature range, making it more sensitive, forming more carbides.
So what does this all mean for preventing this insidious delayed corrosion? How do we stop it from striking after a product is already out in the world? Seems critical.
It is. The primary prevention methods really revolve around material selection. The simplest approach is to use the low-carbon L grades, like 304L and 316L.
Because they don't have enough carbon.
Exactly. These L grades have insufficient carbon to form a significant amount of those harmful chromium carbides, so their corrosion resistance isn't really degraded by the welding heat.
Makes sense. Any other material options?
Yes. Alternatively, you can use stabilized grades, like grade 321, which contains titanium, or grade 347, which contains niobium.
Stabilized. How do they work?
These added elements, titanium or niobium, have a stronger affinity for carbon than chromium does. So they preferentially combine with the carbon to form titanium or niobium carbides instead of chromium carbides. They effectively act like bodyguards for the chromium, preventing its depletion at the grain boundaries.
Clever chemistry.
It is. Now, if you must weld the higher carbon, non-stabilized grades, then welding parameters become critical. You want to use low heat input welding techniques and the fewest weld runs possible. The goal is to minimize the time the HAZ spends in that sensitive 600, 850 degrees C temperature range where those chromium carbides form. Faster cooling through that range is better.
Minimize the time in the danger zone.
Exactly. And then there's a potential fix after welding. post-weld heat treatment, specifically something called solution heat treatment.
Solution heat treatment.
Yeah, this involves heating the entire welded item to very high temperatures, usually around 1050 to 1100 degrees C, and then rapidly quenching it, cooling it very quickly, often in water.
What does that do?
This high temperature dissolves any chromium carbides that might have formed, and the rapid quench prevents them from reforming. It essentially redissolves the chromium uniformly back into the steel, restoring the corrosion resistance.
Sounds like a good fix.
It can be, but it has significant practical difficulties. Heating massive components to over 1,000 degrees C and then quenching them isn't easy, and there's a very high risk of causing significant distortion or warping of the welded component, so it's often impractical.
Wow.
Material selection is usually the preferred route.
Right. Much better to prevent it in the first place.
Right.
So wrapping this all up, what does this mean for you, the listener, who might encounter these welded structures every day? It feels like it all comes together, doesn't it?
It really does.
Understanding these specific mechanisms behind weld defects, I mean, whether it's hydrogen making steel suddenly brittle or tiny impurities creating weak spots during solidification, or these internal plate flaws tearing apart, or even chemical changes leading to corrosion later on, it's all absolutely crucial for preventing really costly and potentially dangerous failures.
Absolutely.
It's about designing with foresight, choosing the right materials for the job, and executing those welds with real precision and care.
Indeed. Knowledge truly is power in preventing these issues. And it's important to remember that unifying concept we talked about in most cases. By effectively addressing just one of the contributing factors for each type of defect, you can often prevent it entirely.
Just break one link in the chain.
Exactly. It encourages us all, I think, to think critically about how seemingly small details in material science and manufacturing processes can have absolutely massive implications for the integrity and safety of almost everything around us.
That's a great takeaway. So next time you see a welded structure, whether it's a skyscraper reaching for the clouds, maybe a pipeline stretching across the landscape, or even just the frame of your bicycle, take a moment. Appreciate the invisible science and the meticulous care that likely went into making that connection strong. And maybe think, what other hidden engineering marvels are we often unaware of, quietly keeping our world together? Something to mull over. We'll see you next time for another deep dive.